Hi, Eddie. Can I get a sound check or Tunji? Anybody? Hey guys, can you hear me?
Hey, Professor, how you doing?
Okay, good, thanks. Where is Nathaniel? I have to apologize to the man. Hey, Nathaniel, sorry, man. I kicked you out of the. I like logged in, and then I'm like, oh, there's nobody here. I must have gone into the wrong Zoom. And it's just as I hit like N to try it again, I know you logged in, so I'm sorry about kicking you off.
No, it's okay, Professor.
Let's all situated. Man, I don't know if you guys have not discovered this thing. This is like a secret weapon. My brother introduced it to me 2 weeks ago. Like Trader Joe's has got these chocolate bars with like I think it's about 85 or 90 milligrams of caffeine, you know. So I was just like totally wasted. I got back to the house around like 3:34. I was like in San Dimas, like doing some bicycle stuff over there or whatever. I got back and I'm like just totally wasted. Ate one of those chocolate bars and like this is like rocket fuel. It's like much better than a cup of coffee. I don't know why. It's like it's got the same milligrams of caffeine as a cup of coffee, but it just like I don't know what it does. But anyway, so if you guys need some help with your midterms, really highly recommend these chocolate bars with the caffeinated chocolate bars. You heard it from me. Now you guys probably already know all this stuff. Okay. Well, so guys, we were talking about power consumption, and so okay, so where we ended was this really important equation about power consumption in CMOS circuits. By the way, have you guys taken, as an aside, because we're going to confuse you, have you guys taken analog CMOS design? I think there is a class at Cal Poly that teaches that. Anybody taken that by any chance? No?
No, definitely not.
Okay. So because the reason I ask is because the noise, there's just something magical about CMOS. And for some reason, it occurred to me like last lecture this here that it's kind of similar, and it has to do with noise in CMOS sample and hold circuits, which are, sounds like it's just a circuit, but when it comes to analog CMOS design, like sample and hold circuits are just like used everywhere. And it turns out that it doesn't matter the size of your transistor that uses CMOS sample and hold. The noise is only a function of the capacitor you use to sample, which is interesting. But to bring it back to our discussion, here's another factor in CMOS, is that the power consumption has nothing to do with the size of your actual transistors. So the power consumption of the circuit is only a function, if you're looking at a circuit element, is only a function of the capacitor that you're charging and discharging. nowhere in this is like a equation that's worthwhile memorizing, CV squared F. Okay, so it's got this capacitance that you're charging and discharging. Again, nothing to do with the size of your transistors. It has the power supply that's connected to your circuit. And in fact, it's a very, very strong function of the power supply. You see, it's got the square term on the supply. So this is like, think about what this means. We're playing around with a 0.18 micron TSMC process. So VDD there is 1.8 volts. So I think 1.8, so VDD squared is 3.6 volts squared, something like that. Better double check this. Of course, I'm wrong. Thank God. Well, 3.24. Thank God for calculators. 3.24. And then, off and on, we see examples of like a 65 nanometer process that's got the VDD of 1 volt. So VDD squared is 1 volt squared. So if you have the same circuit operating at the same speed, driving the same capacitor, but made in this process, the 65 nanometer process versus the 0.18 micron process, just because of that, you've reduced your power consumption by a factor of over 3x, which is like a gigantic number. So all you did is, went from this process to this process, same circuit, doing the same thing, driving the same load. So this is like a very, very strong reason why power supplies go down, because they really, really help your switching power consumption. So you can't go down forever, unfortunately, because as we saw during the leakage current lecture, as your power supply goes down, your threshold voltages unfortunately also have to go down. So you get, again, the speed is a function of the supply voltage, although the power consumption isn't. So as your voltages go down, your threshold voltages also have to go down to get the same current out of your transistors, and the lower threshold voltage means a higher leakage current. So so long story short, if you look at, so now, we're at the, 5 nanometer, the latest node is like 3 nanometer, which is mind-boggling. But the power supply is still like around 0.9 volts. It's not like the power supply is at 0.1 volt. And the other reason for power supply staying at these higher values is that, as we saw last time, your noise margin, you want to keep your noise margin. If you start going down further, you're going to degrade your noise margin. So what happened to the power supply is it dropped from 3.3 volt to 2.5 volts to 1.8 volts to 1 volt, and it kind of like straight at this sort of 1 volt level. And a big reason for this is the power consumption. So again, huge difference between a 1.8 volt power supply and a 1 volt power supply in terms of power consumption. Okay, so the other advantage of going to a smaller node in terms of power consumption is a lot of this capacitance that you're driving. So imagine, when the example that we're using for our projects, that capacitance is as you'll see, that capacitance is representing a load capacitance outside the chip. So it's outside the chip, it is what it is. That capacitance is what a routing capacitance between chips. But when you're, talking about capacitances inside a chip, a big part of that capacitance is the routing capacitance, the metal wires that you're connecting the circuits to. So as you make your processes tighter and tighter, these circuits get packed closer and closer together, and you're also reducing your capacitance. So you're reducing your power supply, which you get a huge effect, huge improvement. And then you're also you're reducing your capacitance because you're packing stuff closer together. And the frequencies, it is what you need it to be at. It's just, that's not going to change. It's whatever function it is. But, because of power consumption, the frequencies of chips, as far as I've seen, are sort of stuck in the 1.5 to 2.5, 3 gigahertz sort of clock frequencies. Okay, I mean, when I look at like Apple or like you look at cell phones and stuff, that's sort of what they are. They're at like, although you could make devices that run at like, I don't know, 30 gigahertz, 60 gigahertz, whatever it is, the power consumption would just be too high. So they're kind of stuck in that. But anyway, long story short, this is a very important equation, CV squared F. And, what can I say? Very, very big dependence on the supply voltage and no dependence on the actual sizes of the devices. The size of the devices determine how fast you charge and discharge, means they determine how fast you can run the circuit, but they don't have anything to do with the power consumption of the circuit. That just, to me, it's a kind of an interesting thing that they're nowhere in this equation. Okay, so if this was all there was to it, we'd still be kind of in trouble, because if you even, we said, look, we'd be in trouble from a chip standpoint, because we said, like, even if you have a chip, you've got 20 billion gates, transistors, whatever it is, billions transistors of devices. Only at any one time, a small part of this chip is working, and the rest of the chip is like in standby mode. So, say a small percentage of this chip, let's say 5%, 10% is operating. And so in another operating mode, there might be, another part of this chip operating. So maybe this is like the ALU doing some function there. Maybe you'll do a memory access kind of in another time period. And so you're turning things on and off. Okay, so that really helps. Stuff that's off doesn't have any switching current. Stuff that's completely off. But still, if this was just chugging along at the clock rate of whatever, 4 gigahertz, you'd still end up with a big power consumption. So for our assumptions or our back of the envelope calculations of power consumption, though, we also have to think about how much switching we get. Okay, so let me give you guys an example. So let's say we have a clock. So let's say this is time, and we got a clock, we got high-speed data, and then we have typical data. So, a clock by definition is the fastest switching. You're not going to get anything in a circuit that's faster switching in a digital circuit than a clock. Let's hope not. right? Because this is what's sort of setting all your flip-flops and all that stuff. So it is the fastest switching thing. So, and remember that you only burn power on one edge, okay? When the input, actually it's on this edge, when the input goes from high to low, as if this was an inverter, right? If this was an inverter. So let's say that inverter had clock, inverter 1, had clock going into it, inverter, sorry for my handwriting here, guys, inverter 2 had, you know, high-speed data, and inverter 3 had the typical data. Okay, so this only burns power. Do you guys remember all this stuff? So we said the supply only sees current flowing to charge this capacitor when the output is going from low to high as you're charging this capacitor. After that, it's cut off, and then we discharge the capacitor. The overall heat gets distributed, the heat power consumption gets distributed over this whole period, but the actual power draw from the supply only happens when the input is going from low to high, and therefore the output is going from, low, when the input's going from high to low, and the output's going from low to high. So you're gonna have the maximum number of those cycles are gonna be happening, and that'll be your clock, okay? So let's say your clock frequency is F. So whatever sees the clock, all these guys, their power consumption is CV squared F, which is your maximum clock. And they'll have different capacitances and so on. Okay, so now by, let's say you have you have synchronous circuits that you're gonna have, we're gonna get into those flip-flops, whatever. So they're only gonna switch on one edge of the clock. Okay, so the fastest data can switch is half the clock rate. So let's say I'm gonna have data that switches on every rising edge of the clock. So, I could have that, be that. It's only gonna, even if it switches on every clock period, it's gonna I screwed that up? Okay, like that, right? So the high speed data is only gonna be at CV squared 1/2 F. And it turns out that typical data, or a number that people use to estimate power consumption for whatever it's worth, obviously because it's an estimate, it's not going to work in every case, is 1/10. Okay, it's that a typical data is only going to switch every 10 clock cycles. So whatever that is. So 1, 2, 3, 4, 5, 6, 7. I didn't draw enough clock cycles, but like whatever, something like that. So typical would be CV squared 1/10 F. It's just not gonna be sort of, again, if you guys have written Verilog code or whatever, not every node is constantly switching, right? You have like stuff that's chugging along, and then stuff that's switching very, very infrequently. So they've come up to represent this concept of the activity factor, and that is alpha. That's the name of it. And for a clock, this activity factor is 1. So this alpha would be sort of, I didn't write it, but it'd be a 1. In this case, for if you got a high speed signal, you'd have 1/2. So if you just as alpha would be 1/2, in this case it'd be 1/2, or so on, but like a typical number is 1/10. So that's for estimation, you kind of use that. Any questions about that, guys? So if you don't use that activity factor again, you're gonna, even though, you know, you're assuming most of the chip is dormant, still you're gonna end up with a big number, and we'll see, too big of a number. Okay, so the other thing, I think we already mentioned this over here, it's saying the same thing over and over again, is the crossover current, the most of the current power, and therefore the power is coming from charging and discharging this node. There is a little bit of current that goes straight from supply to ground. It's called a crossover point, is when both N and P are on. It happens kind of around here, right, where the input is transitioning from high to low or low to high. Right here and right here, both N and the P are on. So you get a little bit of blip of current, okay, going across, but it's basically, we're saying that's a small number compared to the current you need to charge and discharge this capacitance. That's all this slide is saying. It's kind of this like north, okay. Okay, so this is like the total power consumption. So the switching power, okay, is the same as our dynamic power. Okay, so the dynamic power comes from the switching load capacitance and the short circuit current, and we're saying sort of ignore the short circuit current, only look at the switching current, and that is CV squared F, where alpha is the activity factor. And that, you know, depends on your circuit, but, you know, say, it depends on the circuit. So I set an average value is 10, maybe that's for logic, you know, maybe if you have memory, you'll just have to kind of think around roughly when you're estimating the power consumption of some block, you know, how much activity am I expecting in this block? You know, again, we're assuming you're architecting that block or trying to think about what the functionality of that block is and trying to come up with a power consumption estimate. Okay, so that's the dynamic power. But as we said a few lectures ago, used to be that if a CMOS logic gate was not active at all, there'd be no power consumption. But because of the leakage currents, that as the process nodes are getting smaller and smaller, the leakage current is going higher and higher. And so it's become more of a factor. Okay, let me just say this again because it's a little bit confusing. This is what example should I give? You know, this is like a many factor problem. The endpoint of this problem, well, the goal has been to pack as much functionality into a piece of silicon as possible and get it to run as fast as possible. Okay, so that's the goal. And as it's the goal of every generation of, you know, every process generation going back to like 1980, say. And but like once you kind of like push on something, some other thing causes you a problem. So okay, what is the limiting factor? So let's think about it. So I'm just sort of iterating what I just said. So you know, we want to cram as much functionality into same chip, more functionality. Or another way you want to look at it is you want to put same functionality into smaller silicon. Why is that? Well, like going back to our maybe second or third lecture, a smaller piece of silicon costs less. You're paying, you're paying a certain amount for your wafer, for your silicon wafer. The factory does not care how much stuff you put in there. They're just selling you that wafer for a certain price. So if you can harvest more chips from that given wafer, each one's going to cost you less. It's just all there is to it. And as process technologies get more and more advanced, the wafer price goes up a bit, but it's not going up as fast as that. It's not like a 65 nanometer wafer does not cost like 50% more than a 90 nanometer wafer. Okay, so the goal is, if you can, the processes were shrinking because this would allow you to put more, basically the cost per function is shrinking, is the way to look at it. Okay, and it all comes down to money, right? How much, so that was the idea. So you want to shrink it. And so what's setting a limit to how much stuff you can cram into a bit of silicon. For a while, it was the size of the circuits and all that stuff. Again, pretty quickly in the early 2000s, this like limiting factor ends up being power dissipation. You just cannot economically remove the power from the silicon past a certain power consumption point. You have, we'll talk about this a little bit more in the next few lectures, but you have like air cooling, then you have liquid cooling and so on and so forth. But again, liquid cooling is expensive. It's, physically large, hard to do liquid cooling in your cell phone. Maybe you'll do it in your gamer computer or something like that. Anyway, it's hard once you get past a certain point. It's just physically hard to remove that power. Okay, so what do? Well, the power consumption is CV squared F, whoops, F. People aren't going to go down in frequency because that's kind of reducing your functionality, really. If your chip is running, your block is running slower, no one's going to like that. So you reduce the voltage. So reduce the supply. Okay, so now I reduce the supply, right? But what happened if I reduce the supply? If I reduce the supply, remember my, if I have an inverter, let's say I did not touch the capacitance, my capacitive load. So the amount of current that my inverter charges and discharges, this current is in saturation. The drain current is either, this is, the whole thing up so you guys don't have to remember. Mu Cox W over L over 2, VGS minus VT squared, or it is mu Cox W over L VGS minus VT minus VDS over 2 times VDS. So whether it's in saturation, basically we saw that, as you're transitioning, sometimes you're in saturation and then sort of transitions to linear, doesn't matter. Basically the gate source and the gate sources are VDD, right? Because my gate is always the supply of the previous inverter. So this is really VDD. Okay, so I'm going to replace those with VDD. So let me just. Okay, so Now look at what is happening. Again, this is like a simplified equation and so on, but just bear with me. It's like a first order type of description of the problem. As my VDD shrinks to keep the power consumption low, my current is starting to shrink. If I keep my threshold voltage the same, okay, as VDD is going down, this VDD minus VT gets to be a smaller and smaller number, means for the same size device, my current is shrinking. And that current tells you how fast you can charge and discharge this capacitance. So my process is getting slow as my VDD is shrinking, which is not something I want, because the customer is not gonna want to hear that, doesn't want to hear I can't go as fast. Okay, so how do you respond to that? Well, you respond to it by reducing the threshold voltage of your devices, because the important thing isn't VDD, it's this VDD minus a VT, or VDD minus a VT here, and these VDSs are also VDDs, but anyway. So okay, I can crank up my current back up by, if my supply shrank, I'm going to reduce V sub T and get some of that back. Okay, great. So now the problem is that, as you saw, let's see, VGS gate source, I sub D, and this was in the log domain. I think this was linear. We saw that instead of, if you plot I sub D versus VGS, remember this is VGS, gate source voltage. What happens is, instead of current coming down and doing something like this, going to 0 at V sub T, what was happening was that, so remember this is a log scale, okay? What was happening is, and I'm doing this really badly, guys, but basically you continue to have this sub-threshold current. The reason it's called sub-threshold is that even below your threshold value, you get some current, okay, that is going down by a factor of 10 every 100 millivolts. Okay, so if I'm at V sub T minus 100 millivolts, this subthreshold current is a factor of 10 less than I was at V sub T. Okay, so what's happened here? As my V sub T shrinks, I don't have what it, eventually I'm going to end up at VGS of 0. But let's say if my VGS was, V sub T was at, imagine my V sub T initially, initial V sub T was at, I don't know, 700 millivolts. And this was 700 millivolts for a 1.8 volt process. Now to get some of my current back, because my supply shrank, I'm going to make V sub T 300 millivolts. So from 700 millivolts to 0, I have 7 100 millivolt steps. So how does this go? So my leakage current, so compared when I'm at VGS is equal to 0, and make a terrible mistake here, my I sub D is 1 over 10 times 1 over 10 times 1 over 10 times 1 over 10 times 1, 2, 3, 4, 5, 6, 7. It's that much less than I sub D at V sub T. You guys with me? This is getting really confusing. Wait, are you
Yeah.
guys, yeah, okay. And in this case, again, all things being equal, I sub D is 1/10 times 1/10 times 1/10, until I just run out of 100 millivolt steps, right? So this leakage current is the, whatever that is, 10,000 times less than this leakage current. Okay, so if I shrink my threshold voltage from 700 millivolts to 300 millivolts, all things being equal, I'm going to have 10,000 times more leakage current for this case than this case. So as I reduce VT, my leakage current goes up. So my power consumption goes up. So, and here we go, this is like sort of this endless loop of, it's kind of like, I don't know, like hacker battles or something. Every time you do something, you improve something, and then something goes bad, and then you kind of like go in another direction, and then whatever. So this is why we are, I was sorry about that, this long-winded story about why we are, give you a rough idea about why we are where we are now, which is that the static power, the majority of which is coming from the sub-threshold current. Okay, why we're in the situation where now this is noticeable compared to the dynamic power. The static power now is, maybe it's only 10%, maybe it's 25% of dynamic, but it's not zero. Okay, so but that's why we are where we are. We had to end up reducing threshold voltage to get some speed back, and that cranked up the leakage current. And this is like a very, very, very oversimplifying what's going on, but at the CEO level, that's what's going on. Okay, at the executive level. So, and then typically you don't really worry about these things. It's all about the sub-threshold leakage. But that's where we are. So we have a sub-threshold leakage component, and then we have this switching circuit component. Okay, so now let's look at let's do some the dynamic power examples are very simple once you get your hair around it, but it's easy to get confused. Okay, so let's try to look at this together. This is like yeah, let's try to look at it together. So this is what you'd be faced with kind of when, again, remember, with this stuff, with power consumption estimation, with speed estimation, with area estimation, all the stuff we're doing in the class, in this class for chip design, VLSI design, we are going over techniques that you're using up front before you start the design to give you guidance about architectural choices. When you already have the design, you have computer-aided design tools that you put in your basically once you've got your Verilog code, you can give it like typical vectors to your computer-aided design tool, and give it a bunch of different vectors and sort of typical inputs, and it's going to sort of spit out like sort of average power estimates of power consumption. Okay, so that's what you would do at the end. But at that point, it's too late if you screw it up, if you made the wrong choices. Now you're months into your design process and you've got the wrong answer. You've painted yourself into a corner, and worst case scenario, you got to rip everything up and start from scratch. Okay, so that's not what we're doing in this class. We're looking at the point where you're at the beginning of your design cycle, and you are me, whoever, we're trying to estimate if we did this, what is the power consumption of, estimate the power consumption, and what is it going to look like in this process? What's going to look like at this frequency? What if we made this a little bit smaller, that a little bigger, or whatever? Okay, so this is that kind of example. So what this says is, I think, this is, maybe it's more likely that you would be faced with coming up with an estimate for a design block. But let's say the design block that we're gonna be assigned to estimate the power consumption of would have this characteristics, right? It would have, so, we can think of it as being, it depends on the size. Maybe it's the full chip, or maybe it's a block in a chip that does some logic and has some memory. Okay. And we'll see why there's these two divisions. Okay. It's because you're making really gross estimates. Okay. So for example, you're saying I have roughly 50 million logic transistors, and how would you come up with that? Well, so you think of the functionality that you have in this chip or in this block, and you are almost never starting anything from scratch, right? They'll have a bunch of functionality. You'll have, again, it'll have a I2C interface. It would have some different chip blocks that are already, like, if you were gonna design a circuit with 50 million logic transistors from scratch, it would take you the rest of your life and the rest of your children's life and so on. So almost always you're starting with blocks that, that are getting grandfathered in terms of the functionality, or you can kind of estimate, well, it's about this functionality that you're asking me to have in this, Mr. Customer or Mr. Marketing Person, is about 50 million logic transistors. Okay, how'd you come up with that? Well, I got this block, got that block. This block is, 100,000 gates. Each gate has, roughly has 4 transistors, and whatever. So, and that's how many transistors I have. Okay, and then you're coming up with an average width. So again, remember the lengths, you'd go for minimum length. So you're coming up with an average width for a logic transistor in your logic gate. How'd you come up with that? Again, experience, sort of average, you're throwing up some numbers. So this lambda is a constant. We didn't really get into this. The problem is this way of looking at lambdas is a sort of antiquated, no longer applied. But let's say in this case, for a 65 nanometer process, just take my word for it. Let's use a lambda of, what's a good lambda for this? Actually, this exam, I want to make sure I don't give you guys the wrong number. What lambda are we using? It typically ends up being like either 35 or 40 nanometers for lambda. Okay, so that means that, so that's kind of the size. Okay, and then activity factor, you as the designer has decided most of the circuits are not operating, most of them are not constantly chugging along, that on the average, the activity factor is 0.1, or about 10% of the logic is chugging along at any one time. So again, if you don't know any better, this is like, seems like a comfortable number that people use. Okay, so what does this 12 lambda do? So this is assuming that, let's say I'm going to use a lambda of 40 nanometers. Okay, and I'm doing this assumption in a 65 nanometer process. Okay, in this process, and I'm further assuming that most of the load that my gates are driving is other gates. Okay, what do I mean by that? So let's take a look at it. So this is saying that in my average situation, so this is an average case, I have a gate sorry, yeah. So saying this is kind of my average situation. A gate is driving another gate. And it's saying on the average, this gate is made out of transistors that are width is, again, if I assume 40 nanometers, it is 480 nanometers. And length is 65 nanometers. So that's the average transistor in this. Okay, why does that matter? Now remember, the only thing we care about when a gate is driving in terms of power consumption, when a gate is chugging along, we don't care what this gate, as long as the CMOS logic gate. We don't actually care about the size of this devices as far as this gate is concerned. We are concerned about what capacitance it's driving. So if I say, never mind the interconnect capacitance, so what I'm saying is this gate on the average, its output is driving another gate. And on the average, that other gate is made out of the same transistor size. So this guy's driving something like along the lines of the same transistor size, okay? And this average transistor has this capacitance. It's got 1 femtofarad per micron capacitance in this process. So that means if I had a 480 nanometer wide transistor, its capacitance would be 0.48 femtofarads, its gate capacitance. Furthermore, okay, so now I have this input capacitance plus, remember this guy, if it's a NAND gate or inverter or whatever it is, it's going to have some drain capacitance, so its own drain capacitance to drive also. And that drain capacitance is going to be 0.8 femtofarads per micron. So that's going to be, it's hard to calculate, 0.8 times 480 is 0.38 femtofarads. So my total capacitance is going to be 0.38 plus 0.48. Or 0.864 per logic transistor. And if I have like 50 million of them, so total load capacitance is 50 million transistors times 0.864 femtofarad per transistor. Oops. Or 4.32 times 10 to the minus 8 farads. Do you guys see where I'm going with this? So this is kind of like you're really doing approximations here. You want to know what is the total capacitance in this block that you're charging and discharging, right? Because this dynamic power, remember it's CV squared F. So we need to come up with an estimate for C, because we already have V squared, right? They told us the supply is 1 volt in this process. So V squared is just 1 volt squared. They told us they want us to figure out the power consumption at a gigahertz. So this is 1 times 10 to the 9th, the F. So power dynamic. Let's put that. So we got this, the problem gave us this, they gave us this. So we're calculating what's the C. They also gave us the activity factor, sorry. So we also have the alpha. So we're trying to calculate the C. So this is known, the voltage is known with certainty, the frequency is known with certainty. The alpha is some estimate of activity factor for the logic. Somebody told us that. So we're trying to come up with an estimate of the total capacitance that would be charging and discharging at this frequency and this activity factor. Does that make sense, guys? I know this kind of sounds pretty convoluted, but you're really operating at like a really high level of, when you're trying to estimate power consumption in these kind of cases. So we're just sort of guessing, okay, this is the total capacitance that might be charging and discharging. Does that make sense? Any questions about that? No. Okay, so you do the same thing then for this memory block. So that's what you did here. You do the same thing with the memory block. Now, interesting stuff about memory. Now notice that typically, so this is static random access memory. The stuff you buy in for your computer is dynamic random access memory. So this is like I don't know, what is it called even anymore? DIMMs. So this is memory outside chip is typically dynamic random access memory. Let me digress for a minute, because I think memory is important. Are you guys familiar with the difference between dynamic DRAM and SRAM and all that stuff? Have you guys heard these terms?
I haven't.
Okay, so let me just digress, because it's kind of important. You guys are going to see this in your life. So you have 2 types of, well, you really have more than 2 types. You have really kind of 3 types of memory. Well, 4 types of memory. So this is a hierarchy, right? So you have what you would call some memory. This is, I'm like way digressing, guys, because we do not have a chapter on memory in this class, but this is like important for you guys. So I'm just sort of I apologize, put the power consumption on hold for a second, but because we're talking about SRAM or memories, I wanted to give you some background. So you have memories. You have 2 types of memory. You have non-volatile memory. And I guess you don't really call it volatile memory, but I guess I don't know what to call it, so I'll call it volatile memory. Okay, so that's the first branch in the chain. So what's the difference between the 2? Well, the difference is non-volatile memory, the memory information stays there even if power goes off. So if you shut down your device, you still have like non-volatile memory is like stays there. So like this is what you use in your I guess it's like flash drives in like your computers now. We don't use hard disk anymore. Okay, like this is not even that long ago, 10 years ago. I don't remember if you guys remember. Don't know if you guys remember, but there was actually a hard disk with a disk drive head and, you know, like a magnetic reading. I don't know if you guys remember that, but now it's solid state memory, okay, in your disks. So solid state storage, okay, and like the people who make this, I don't know, a Samsung, whatever. So this is the stuff when you buy your, you know, hard disk drive or whatever they call it. What do they call it? Disk drive? I don't know what generic they would call it. I always get confused by this, but you guys know what I'm talking about, right? So you buy your you know, you buy your iPhone and it's got 256 gig. So it's 256 gigabyte of this stuff. So even if you shut down your iPhone, the next time you power it up, this info is still going to be there. It's non-volatile. It's like burned in. I want, and you can rewrite it a bunch of times. And this is like, you know, there's different technologies here. There's like NAND, flash is like very, very important. And anyway, so this is non-volatile, then you have volatile memory. What is volatile memory? That's the memory you have, sort of your operating memory, okay? So let's say in your computer, you have, you know, 16 gig of memory or 32 gig or 64 gig, whatever of memory, okay? So now there's two types of that. There's DRAM, which is dynamic random access memory, and you have SRAM, which is static random access memory. Okay, so they both have the term random access in it. And that's because when you guys, you know, again, I don't know if you guys have played with this in microprocessors or whatever, but you can imagine you can go anywhere in this memory. You basically give the memory an address location and you read the value from that address in your memory. And it can be anything. It doesn't have to be in sequence. You don't have to start with location 1 and work your way up to location, you know, a billion or whatever it is. You can jump around, and that's where the random access comes in. The reason for that is kind of a little bit historical, but anyway, so that's the random access. So to separate the two of them, there's the dynamic and the static. And so almost, well, I think it's basically all of the like computer memory or external to the chip memory you buy is dynamic random access memory. So again, like if you upgrade the memory to your computer, I can't really do this with your cell phone really easily as far as I know. If you're an upgrade, you go and buy like a DIM or SIM or whatever it's called now, and you plug that in. Those chips are dynamic random access memory chips. Okay, so why dynamic? Well, it's because they are using a very simple circuit to store the bit info. They're just using a single transistor, each bit in there, and a single capacitor. So each bit is only one transistor and one capacitor. Why are they doing that? Is because they're trying to cram as many bits into that chip as possible. And this is like basically as simple as like a circuit can get. You have a single transistor. So if this basically to write into this memory, you turn on this transistor, you dump a binary 1 into this capacitor, and then to read it, you turn on the capacitor and you kind of go poke at what's in this. So the reason so the reason it's dynamic is because we have leakage currents. Every time you read this, you're basically destroying the value as you're reading it. So it's dynamic in the sense that you have to keep refreshing this value continuously as your chip is operating. So first you power up your cell phone or your computer, and you fill this memory from your non-volatile, your operating system fills this memory with whatever, and you're just chugging along, you're opening up apps, and those apps are, you know, putting all their information on this memory as they're operating. But furthermore, if you look behind the scenes, these memory chips are constantly, they're just chugging along inside the memory chips. They are refreshing, they're constantly running around refreshing the value of every bit in that memory. It's just it's like a never-ending process, because they made it really simple to cram a bunch of bits in there, but there's like this nodes are discharging all the time, and every time you read it, you eliminate it. So it's dynamic. It's constantly, you got to keep constantly touching it. There's a lot of stuff going on. SRAM memory is now almost all the memory on chip is static random access memory. And what is that? Well, inside the chip, so even though you refresh the stuff and you're chugging along or whatever you're doing with your DRAM, you still have to tweak the hell out of this process. So these leakages are even reasonable, okay? Which are like if you try to pull the same thing inside your chip with the same process that you're, you know, doing, you know, creating your, you know, high-speed logic circuits, it just would not work, and it does not work for the most part. So what people do use is this static random access memory that is basically 2 back-to-back inverters. And then I'm really simplifying this. So basically you end up with either 8 transistor or 10 transistor circuits, something like that. So if you imagine this thing looks like a latch, right? So once you dump data into here, you put, I think we talked about this a little bit. Let's say you just want to store 0 here. This makes this point a 1. And this inverter feeding back reinforces the 0. So once you write the 0 here, as long as you don't lose power, as long as you don't shut down this memory, it stays static. It doesn't change. So that's why it's called static random access memory. Okay, so it has a disadvantage that it's big, meaning that given the same silicon area, you cannot, you know, here you got 8 or 10 transistors, sometimes you have 12 transistors for different reasons. Basically, you can, you know, given a certain chip area, you can put in 8 or 10 times less of these than of these. I'm exaggerating, but you get the idea, right? So outside the chip where you can tweak your process, you don't use this stuff out here, okay? But inside the chip, you can't use this stuff because this is also a very specialized process. It would just, everything would just leak away before you even try to do anything with it. So you're stuck with this static random access memory. So this is, did all that make sense? I hope it made some sense for what you guys are doing. So, so inside the chip, upshot is that you have these memories that you're talking about is static, okay? So now, given your limitations that there's 8 transistor or 10 transistor here, you still are area limited. So you basically, you know, if you, and you want to always, you want to have as much memory as possible, or you have a certain memory you need to pack it. So you, what you'll see in memory, this is called the bit circuit. So the other thing about memory, sorry, let me tell you guys another thing about memories. So memories. they have two components. So I think there's some of the stuff in your book. I just don't know if we're going to get to it. So you have the actual bits of storage. And then you have your readout. So in this readout, there are these circuits in here called sense amplifiers. So, and then there's like, you know, there's sort of addressing. So kind of row and column addressing. So basically what you do is you kind of select some row or column, and then you connect this to a bus and you read it out from one readout. Okay, so these memory, these guys are the actual bit things in here. So more or less, you know, basically this being a dynamic thing, these addressing gets a lot more complicated because you have to go and charge and those kind of things, and your sense amps are more complicated. Same idea. So these bit circuits, they take the majority of the area of your memory. And so you want to make them as small as possible, whether they're SRAM or DRAM. So, okay, after that digression, this is kind of going back to this. When you say you know, the circuit block has 50 million logic transistors and 950 million memory transistors, notice that the assumption for the size of the memory, the width of these memory transistors, is a factor of 3 smaller than these logic transistors, because you're going to make them really small to pack them in. They're not going to run as fast. There's some that are only involved for this local feedback, so they don't need to be that big. So on the average, they're going to be smaller. Furthermore, remember that this is a memory. So if you have, you know, 950 million whatever bits, oops, here we go again on the pattern. Excuse me for a second, guys. So even if you have 950 million of these transistors, you're only accessing like 1 word at a time. You're not going to be accessing the whole freaking memory, right? So you're only addressing in any particular clock cycle, you're only accessing a word or maybe 4 words or whatever it is. So you're accessing only a tiny amount of the memory. So if the activity factor for a logic block is 0.1, it kind of makes sense that the activity factor for the memory is significantly less. So it'd be 0.02 is the assumption here has been asked. So again, imagine only 10% of the logic gates are switching in every clock cycle, and only, whatever this is, only 2% of the logic bits are changing. So that kind of makes sense. So you go through the same process. So now you have a smaller capacitance, but you have, you know, a lot more of these memory transistors. You have a lot more of them. They're smaller and their alpha is less, but those are the 2 components you have in your capacitance. So if you look at the solution, it's, you know, I think they use the slightly, okay, they use the lambda of 25 nanometers, I use 40 nanometers. So this lambda is 25 nanometers. I think that's the main difference with my calculation. But basically they said, okay, I have 50 million transistors in my logic. On the average, they are 12 times 0.025 microns, whatever this value is. They're this size, and the capacitance per unit width is this much. And so I get a total of 27 nanofarads for the logic. I have a lot more memory bits, but they're smaller, they're this size. Same capacitance per unit width, but there's less of them. But still, because there's so many more, the memory has, you know, a lot more capacitance. Okay, but The logic has an activity factor of 0.1 times this logic capacitance. I have an activity factor of 0.02 for this memory, but both of them multiply the V squared and the F. And so overall, I end up with 6.1 watts for this chip or this chip block or whatever you come up with. So that's kind of the procedure. It's kind of real back of the envelope calculation. But again, remember, if you don't do this calculation up front to roughly figure out where you are, it'll be too late to, like maybe the end time, by the time you're done designing this thing, this value will be 10 watts or 4 watts, okay? But if you were counting this thing to have a power consumption of 500 milliwatts, boy, you'd be up shit creek by the time you finish designing it, okay? Or you'd have to figure out another process or something to put it in, or operate a lot smaller. So this is kind of the back of the envelope techniques for calculating power consumption. Any questions, guys? That was real around the world analysis of memory and power consumption. Hopefully some of you are with me. Okay, so again, I think this is, I don't know what to say. This is like motherhood and apple pie. That's your equation. So if you want to try to try to reduce power, you can go to, redesign your circuit or your functionality so fewer things are switching somehow. Okay, so again, this class is assuming you're doing things at an architectural level and you have some control over how your block works. So maybe you can redesign your block so there's less switching happening. Okay, capacitance, what can you do with that? I don't know if there's a whole lot you can do with that. Supply, I guess capacitance really comes down to how well you can, well, no, I'm not sure you can do much with that. Then the supply has to do with what process node you're in. Okay, if you're in a 65 nanometer process node, you're in a 1 volt supply. If you're in a 0.18 micron process node, you're in a 1.8 volt supply, and so on and so forth. And then you can try to reduce operating frequency, but good luck with that. It just seems like kind of typically you are where you are in those frequencies. So you need to do a certain amount of functionality in a certain amount of time. Okay, so this is sort of coming down with estimating activity factor. I'm not really going to get into this except, this typical value of 0.1, because I don't know, this is like really, to me, this is this probability analysis and blah, blah, blah is implying that you have a lot more knowledge than you really do at this point. Like you're not operating at the point of, when you're doing this level of calculation, you're looking at your logic like kind of at this level. You're not going, I have 50,000 NAND gates and this many NOR gates, or I would guess, but each one anyway. If you were going to go into it, this is talking about each one of these types of gates has a certain number of inputs and there's a certain number of permutations. So there's a certain probability of switching, and this gives you some activity factor. I don't know. That just seems like it's kind of overreaching with this level of estimation. Okay, so there we are with the, if you have the situation, what you do, okay, with the switching power. So this is at a, if you have a block that's chugging along, what is the power consumption? So now let's look at what you could do at the system level, again, assuming and I'll just talk about this real quick and we'll stop, because this is a really, really powerful technique of reducing power consumption. And it's called clock gating. And so this is, not talking about gates, etc. It's talking about at the block level. And simply the idea is that a clock has the highest activity factor in our circuit. It probably has the highest capacitance, highest capacitive load also of any circuit in your chip. In fact, probably, so typically the clock network by itself is about 25–30% of total chip power. So high capacitance, high activity factor. Okay, so if you can somehow do something about that, it's a huge win. Okay, so what you do is you do this, is you put different blocks in your design into these different clock units and you gate the clock. So when those blocks are not functioning, what you do is, notice this is in the path of the clock, it's not data. So this is turning off the clock. So you enable or disable the clock going to the flip-flops in this entire block using this clock gating circuit. Okay, so let's say this is, this block that's getting gated might be, 100,000 gates, 10,000 gates, whatever. Whenever you don't use it, you disable the clock going to this entire block and you save this entire power consumption. So this is a huge, huge, huge win. And it's something we do all the time. Very effective, this clock gating approach. Okay, so you have to be really careful how you do it, because it's really easy to screw this up also. So you got to make sure, this is also a place where a lot of things go wrong when you do clock gating, because just imagine this enable logic, if it's asynchronous to the clock, it's possible to get sort of, when the clock comes in, you get sort of intermediate glitches here, and then you're totally destroyed. So clock gating is very effective. Just remember the word clock gating, because there is a lot of detail around clock gating, but it's a very effective power reduction. But can be dangerous. Very. If I can count up how many chips we have clock gating problems with, but you just, it's the source of a lot of problems. But you keep going back to it over and over again because it's just so damn effective in reducing power consumption. And again, the idea is you're just disabling the clock, going to into all these sections that you can turn off when nothing is going on there. And it also comes down to the architecture, where you try to subdivide your functionality into blocks that you can effectively turn off from time to time. Okay, guys, sorry to be long-winded, but anyway, I wanted to finish off. The clock gating is just awesome. I don't know, but for very dangerous. Okay, so let me stop there, and we'll talk about a couple other concepts in the next lecture. Any questions, guys?
I have none.
Okay, cool, guys. Well, have a good weekend. Talk to you guys later.
Thank you, Professor.
Thanks. Bye.